Hello, everyone. My name is Sarah Hu. Liz is here as well as our instructor today. And we're going to go over the rest of lesson 8b on our studio, which was the rest of Ordinations part 2. So yeah, there's a lesson in our studio and it's called lesson 8b. And we started it last week. I'll quickly review like what we did last week and bring you up to speed just to see if there's any questions. There's been some conversation in the, I'm going to share my screen now. There's been some conversation in the, our Slack channel about some follow-ups on like dealing with compositional data. And I think that'll be like an ongoing theme, especially as we go through some lessons that are both applicable in Amplicons and in R, or in that we can deal with data in R. So this is lesson 8C, but we're going over the code from 8B, and then this corresponds to Amplicon lesson 5C. So to review quickly what we did last time, you guys can all see my screen now, right? Yes. Okay, so we're going to, let's see. So just make sure that when you are in the BVCN workspace that you make a copy of lesson 8B and then you move it over to your personal workspace, because then I get a disconnect when that happens, when I'm running the command, when there's more than one person on this. So I'm gonna reconnect again. Okay, so I've run through this code already, and so I have everything loaded, but make sure you are starting at the top. We're gonna start at line 220 today but I will, up at the top, I just wanna acknowledge really quickly that this was a code that I wrote with collaborator Daniel, and this corresponds to a paper that just came out with collaboration with the White's Lab, which is I've linked to here. And there's a GitHub that has not only this lesson, but it's slightly different because I've modified the code a little bit. And there's a bunch more stuff in this paper that is kind of along the same lines of like diagnostic tools before dealing with things like ordination. And this is all under the premise of microbial time series data, but it is applicable to other types of data sets as well. So these are the libraries that you need to have loaded and the test data set. So make sure you have all that together. So I'm going to go back to line 220 before we continue. So I'm going to compare to another transformation set, but really quickly, what we did last time is we talked about compositional data, especially in the context of Amplicon sequencing results. And we went over some data transformations, specifically emphasizing log ratio. So that was isometric log ratio, CLR, centered log ratio, and it was mentioned ALR, which is additive log ratio, which is another one that's recommended. And there's been some references on our Slack channel that kind of go into more details of when you might want to use those. We did some PCA analysis, principal component analysis, and principal coordinate analysis, which was the PCA on the distance matrix that was calculated from the count data. So we started with some of the untransformed data, meaning the raw counts that you get from the Amplicon results. We used a Jacquard transformation or distance matrix, and then our distance metric, which is a little more like presence absence. And so if you're approaching that, one thing you might want to think about is, do I care about rare taxa in my Amplicon analysis, in which case Jacquard might be right for you. But then I also went over using scree plots and how to evaluate how many axes you might want to use. And so that kind of left us with doing some 2D plots, and also this is the result that's already on my screen right now of a 3D plot with the Jacquard distance. And then, then we went into a principal coordinate analysis with Euclidean distance. And so that was performed on the ILR transform data ahead of time. And I do want to make a note that's actually really simple. That is the Atchison transformation, where you do a log transformation and then you do the Euclidean distance. And so that's the only thing I wanted to add to last week's lesson. But I recommend starting there if you haven't already. So today we're going to go over one more transformation, and then I'm going to talk about kind of forcing some of this data into 2 dimensions, because I personally would prefer to not publish with this in the main text. I have used this Plotly output in an HTML format, and then been able to like share that HTML file with someone, and then they can interact with the data like I am here, which is really fun. But I think that 2 dimensions is a little more effective sometimes on a single page. So the other transformation that we're going to go over today is the Euclidean. But actually, this is, I think we already did this last week, but I'm going to just kind of, I'll bring you up to speed one more time. So this is again the Euclidean with you perform it on the log ratio transform data already, right? So that's it's equivalent to the Atchison transformation, and then we're calculating the PCOA here. We're extracting the variances using this block of code here. You can actually just see the different axes and then the percent variance that I've pulled out. And the reason I'm doing that ahead of making the plot is that I can make the scree plot, which then allows me to see that what percent variance each of my axes would report. And then I can make some decisions about how many axes that I want to show in a PCOA. And in this case, I determined 3 would be most appropriate. And so that's where this next chunk of code comes, where I'm like actually pulling out the values that would show it along 3 axes, and then using Plotly to actually make the 3-dimensional plot. So that's where we're right now. And some of these plots, I just want to remind you that in RStudio, both on your local computer or here, you can use this zoom function to then, let's see, make the plot a little bigger, and then you can interact with it a little bit more. So something to keep in mind. Is everyone okay so far for loading everything up? Okay. So, so I know this is a lot of commented out code, but it kind of goes into what I was just talking about, where we don't always want to do a 3D plot. So this one line right here, execute that, because it randomly sets a seed. So then some of the stuff that we're doing will generate some random numbers, and so there might be variation in the output, but then we can compare like oranges to oranges for this right now. And right now we're going to use this meta MDS command, which is in the vegan package. And this is going to make a non-metric multidimensional scaling plot. And so this is a good alternative to PCA, because you have your transform data of some kind, and then you're asking meta MDS to actually put it into the number of dimensions that you want. In this case, I've listed 2. And right, so the NMDS is taking really highly dimensional data, and it's putting it into the desired number of dimensions, and it's going to do its best to preserve all the pairwise comparisons. That means that it is actually is very highly sensitive to outliers, though. And so if you know that you have outliers in your data and you want to remove those, then you probably want to do that before this. And the other thing is that the values that you get after you do this NMDS, you can compare that internally within the NMDS plot, whereas the PCA plot is taking your existing values and trying to put them into a space where they can be visualized in the PCA. So those are kind of the main things that I think about when I'm doing an NMDS, or kind of trying to compare some of my PCA versus NMDS. So right now, this is a kind of these 2 from above lines kind of show you where the code is coming from. The first one is doing the NMDS plot, putting it in 2 dimensions, and I'm performing this on the Euclidean distance matrix that I have, which was calculated from the log ratio transformed. So I'll execute that. And then I'm doing the same thing, but now I'm performing it on the Jacquard distance matrix, but this was actually calculated from the raw count data that I have from above. And so this is running through several things here. And the main reason that I do this is that now that I have these two things that I want to compare. And this is, I was alluding to this a lot last week too, where I wanted to look at the stress. comparing these two values, this is telling me that the Euclidean is a little bit more appropriate or more parsimonious to show the data, because ideally we want to pull out the stress that's going to be closer to 0. So that means that when you force your data into these two dimensions, how much stress are you putting on all these values? So the other thing to point out is that the axes for NMDS are more arbitrary, kind of goes back to why it's more like internally comparable. And so I don't need to pull out values to and then plot on the X and Y axes. But here I can actually work. So I'm going to move forward with making an NMDS with the Euclidean distance matrix. And so I'm going to pull out these points. And again, you can always use the NMDS to actually see what kinds of things you can pull out from your NMDS R object. Another thing I wanted to point out is that this was done in the using the vegan package, and so there's a really simple plot function where you write plot and then you can put in the result of the NMDS. This states down here that there's no species scores available. This is a really simple NMDS that it automatically generates, and I do prefer, just it's my personal preference, to pull out the points like I showed previously, because then I can use the ggplot syntax to kind of add the color schematic that I want. And this is just how I do it, but there is an option to actually learn how to use this base R plotting function, but I'm not gonna go over that today, but I wanted to point it out because I do often use it to just kind of do a quick glance at my the NMDS that I get out, or the PCOA. Actually, you can use it with the above PCOAs that we calculated. And I just want to make sure it looks kind of okay before I spend the time to actually go through with pulling out the values and doing the ggplot. So here I'm extracting all the points. They're listed here. Again, these are my sample names. And so this next block of code is making that a data frame, pulling these out from the row names index, and then separating it so I just have 6 p.m. and 10 p.m. for instance, instead of this preceding x1 and underscore, and making that into a data frame. But then here, actually take a look at the data frame as well. Looks pretty similar to the points up here, but I've pulled out just the 2 axes that I want to show. And then here I'm actually executing the ggplot function, where the X and Y are the MDS 2 axes, and then I've assigned color to be time of day in this case. Oh, and this is actually the end of my lesson officially. This was a little short today, I guess. So I wanted to go over a couple things that we did not explore, which is what to do with zeros, and also making sure I alluded to dealing with outliers previously. And that's something that you also need to be aware of before you go into plotting all these and things you can play with. And so I recommend in terms of best practice, what I would do is I would kind of go through a lot of this code on my data. And again, I might start to identify certain data points that might be outliers. I might run some other tests to kind of determine if I can pull those out. Look at the raw counts in a bar plot format, for instance. And I would probably go all the way back up to the top here, where the first thing I did from my input OTU table, which is shown here now, was actually do this QC and filtering. And at this step is when I would actually pull out the outliers and move forward. This lesson was kind of short with the rest of this code. But Liz, if you have anything to add, especially when it comes to dealing with zeros and outliers, I know that the ordination lesson that you did was kind of based in phyloseq, which is something that I also use. And I kind of just use all of these approaches to see how I best want to represent my data, or what best distance matrix seem to work. So any other best practices that you want to share?
No, not necessarily. I think maybe since you're talking about outliers, I actually have a question for you.
Okay.
When you are looking for outliers, are you talking about entire samples that you consider an outlier, or OTUs or ASVs?
That is a great question. Right now, I'm talking about individual samples. And I think just as a quick survey, the last couple of data sets that I'm currently working on and have worked on had an outlier because it was when I looked at how many sequences were recovered, it was like a couple hundred sequences, while everything else had over 8,000 sequences recovered. So I knew that there was an issue with that sample.
Mm-hmm. So you do it based on like raw reads that are reported per sample, and then also how they look on an ordination?
Well, I think when I start with ordination, my two modes of thinking is like I'll start the ordination with every sample and go through it. Right now, this data set does not have any blanks, but one example is that I would run the blanks through the data set to make sure the blanks do kind of fall outside of some of these plots. And then I'll go back and, then you can actually see, and the decontam package with phyloseq actually does a similar thing in terms of looking at library sizes. And then you can start to compare things like library size of your blanks, same with samples. And so I maybe it's a little more manual, but if I see an outlier start popping up, then I'll go back to the beginning and kind of try to diagnose what happened.
Mm-hmm. Yeah, that's the nice part about working in R. So we actually have a question in the chat. How do you choose which method, Jacquard, etc., to analyze with?
That's a good question. I think that all the code that I'm showing you today is my first pass at everything. So I'll do pretty much everything here just to kind of see what's happening with my data. But the Jacquard versus the Euclidean, it really depends on if you're okay with the kind of the more presence absence space that Jacquard offers, because has to do with rare taxa. In the case where I'm looking at hydrothermal vent sites, actually right now, I'm interested in something that's rare at one vent site compared to another, because one thing I want to know is if that taxa is present even at low abundances at one of the vents and is only present in the vents but not present in the background. That's really important. So if I start ignoring the rare things, I could lose some of that signal. And so Jacquard in that type of question is more appropriate. Whereas Euclidean is going to be more sensitive to the entire composition. And like literally the way that I kind of keep that straight in my head is that the Euclidean requires the log transform data. So that means it's relying on how the composition of the data. And because the data is compositional, you have to do that log ratio transformation ahead of time.
Okay, and we got the response. Thanks.
Awesome.
Any more questions?
I think the only other thing I wanted to ask and just kind of confirm, I guess, with you, Liz, or see what your experience is. The one thing that came up, and it was said a couple times on the R Slack channel, I think this kind of went through and discussed rarefying or subsetting or something, and how that's kind of, or going to relative abundance before doing some of these transformations, and how that's falling out of fashion a little bit. What do you think?
Yeah, it's constantly changing. I mean, I think relative abundance is fine for plotting, so I still use it a lot for that.
Yeah.
But I never use it for statistics unless one of the transformations you're doing is a transformation of relative abundance data. So like, for example, I think the Hellinger transformation uses relative abundance instead of absolute abundance.
Oh, yeah. Okay.
But yeah, in terms of which transformation, I think it always depends on what you want to do, and also like the current knowledge, right? There's always something new.
Yeah, there's always something new, and it's almost good that there's like more tools available. Like I know that when I was analyzing my first set of Amplicon data, I did not know that a lot of these tools existed, or that this information was as important as I now think it is. So
Yeah. Yeah, and like we said the last time, I think you said this the last time, there's so many tutorials now, and if you go through those tutorials, they emphasize these things, so that's good.
yeah, for sure. Okay, awesome. Well, I think we'll try to keep this lesson, or we'll keep this lesson pretty short. If there's any other questions or anything that you want to see in a future lesson, Amplicon and or R based, or if there's a question about this code right now while you have me, let me know. Okay. Well, with that, as always, the R channel is open at all times, and we will have this lesson posted as a part 2.
Thank you.
Awesome. Thank you, everyone.